case when we have very fast convergence. This is what I call, and in numerical analysis, heuristic study of the rate of convergence. Heuristic means by experiments. We don't have an analytic rate of convergence. We don't have an analytic rate of convergence in the sense that we can say this iterative method have the rate of convergence, let's say this one or something like that. There are few results in literature to give such evaluation. So now I return to what I presented yesterday about saturated and unsaturated mappings, classes of mappings. I told you yesterday that when I apply the technique of enriching mappings, contractive type mappings, I started with non-expansive. Then I took strictly pseudo-contractive. Then Banach contraction and so on. But this was, after a while, I realized that what I thought it's a new class, enriched strictly pseudo-contractive mappings, I realized after a while that it is not the case. So there is no progress when we try to enrich this class of mappings. So this was, how to say, this lecture of mine for the first part would be entitled How to Learn from Failure. Because we should do this. So it was a failure. I thought I enriched this class, it was not. I said, oh, this technique is not useful always, so nothing is useful here. So after a while, I reconsidered this situation and I just proved this lemma. This is in the paper I mentioned. So we have a class of mappings, C. We enriched it, this is denoted by CE, but if C is an unsaturated class of mappings, any unsaturated class of mappings could be non-expansive, Banach contraction, Canaan, and so on. The class CE is for sure saturated. So this means there is no any chance to progress here. So this was the explanation. I didn't know at that moment that strictly pseudo-contractive mappings are enriched non-expansive mappings, and then I prove. And here is the proof, very simple proof. We have a map U here. Because it is here, this means that there is a map T here, such that U is the average map of the identity operator and T for some lambda. And then it is easy to see that if we try to enrich U, this means we construct this mapping U mu, then what happens? We compute this and we get this. If we denote this by another, let's say lambda 1, we see that U exactly this one. So it's nothing new. Nothing new. We are in the same class. So keep in mind, any enriched class of mappings is saturated. So this was the moment I realized that we cannot enrich strictly pseudo-contractive mappings. And that's very important. The challenge is to know which class is already saturated or not. So this was the next step, and what we could do. So I like very much this proof. When I realized this, I anticipated that this is the situation. I tried to prove this, and this is the proof. The proof is very nice. Really a nice proof, and I would like to share with you. Maybe you will agree. So we want to show that the class of strictly pseudo-contractive mappings is a saturated class of mappings because the class of enriched non-expansive mappings. And to prove this, we take a strictly pseudo-contractive mapping T. We use this, but we have this only in Hilbert spaces because here is inner product. Okay, is the inner product. So inner product, the norm square norm is the inner product of the same quantity twicely, and then when we compute, we get norm of x minus y square and the norm of this, and 2 times the inner product of x minus y, tx minus ty. And if we use this in the case strictly pseudo-contractive definition, you have seen this, I write for convenience, is plus k norm of x minus y minus tx ty square. So this is the definition of strictly pseudo-contractive. Here it's 1, and here is k, which is less than 1 in the definition. So we include this in the definition, and we get this inequality. This means the norm of tx ty square is less than 1 plus k over 1 minus k. Instead, here we don't have 1, but we have this quantity, and because of using this identity, we are led to this expression, including the inner product. Now is the moment, this is very nice moment, how to anticipate. We should add this quantity in both sides. We add this quantity, look, this is intended to neutralize this term. So we add this term plus this term, which will be needed here. And then what we get? We get this. In the left-hand side, we change. In the right-hand side, this one disappears, and we get this coefficient plus this one. This means we get this quantity. And if we do some transformations, it is easy to see that we denote B this quantity. Okay, I did some more transformation here, and it is easy to show that this is actually B plus 1, and we were square, and then we take the simple expression, and we get exactly the definition of the enriched non-expansive mapping. Exactly. Very nice. And then if you want to convert, to prove the converse, we just go back because all transformations were equivalent. So if we want to show that any region non-expansive is strictly pseudo-contractive, we just go back and we reach the equality for strictly pseudo-contractive mappings. This proof is included in this paper, Fixed Point Theorems for unsaturated and saturated classes of contractive mappings in Banach spaces. And this is a paper I mentioned with the failure. So this paper has no novelty. This is the conclusion, has no novelty. I realized after it was published. It is why? Because I did not follow one of my personal principles to give an example. So I was searching for an example. I said, okay, some example will exist, but because this was presented to a conference, I did not spend too much time to construct such an example. If I would wait a little bit, I would realize that the class of strictly enriched, strictly pseudo-contractive mappings is saturated because it is the class of enriched non-expansive mappings. So that regarding the how to learn from failures, I'll show you later, a little bit later. The same happens with the class of Q non-expansive mappings and the class of demi-contractive mappings. I've already shown that this is included in this one, and we have here a map, maybe it was T5, I don't remember, which is not in this class. So these are independent classes of mappings, and this is the relation. So this is the definition of a K demi-contractive map. It is needed to ask from the beginning that the set of fixed points is non-empty because we have included this, we have in the definition. So it is demi-contractive if there exists a positive number k less than 1 such that we have this definition. Look, if we take here y equal y star, which is a fixed point of t, what happens? Here it's tx y star, here it's x y star, and here it's y star minus y star plus t y star is x minus tx star. So the class of demi-contractive mappings is more general than the class of K strictly pseudo-contractive mappings, because these ask to be fulfill this inequality for all y, and here is just for the fixed point, just for the fixed point. So this is clearly DC. It's a more general class, not only of Q non-expansive, but also, as I have shown you, strictly pseudo-contractive. This is the definition I mentioned yesterday, done by Hicks and Kubitschek in this paper, Journal of Mathematical Analysis and Applications, this volume 1977. And I mentioned also the contribution of my friend Professor Maruster, published in the same year, Proceedings of American Mathematical Society. And look how beautiful is mathematics, how apparently different concepts meet after a while and they turn out to be the same. And this is the case. Look, Professor Maruster, he has a very nice story. He's a mathematician who became a computer scientist. And he worked he was a pioneer of computer science in Romania. He worked in the team to build the first computer in their university, West University of Timișoara now. And first he was a mathematician. He did his PhD in mathematics, but he taught computer science and numerical analysis for more than 40 years at this university, West University of Timișoara in Romania. And a very interesting coincidence. After he graduated university, he got position in my home city, in Baia Mare, but he was far away from the western part, and he married a lady from Baia Mare, so he's somehow related to this, to my home city. So he introduced the concept of mapping satisfying condition A. Look at this, and look at this. Are they similar? No. Anyway, we have here a term, a constant m positive. We have here a constant k which is less than 1, but these two conditions are equivalent. And this was a PhD student. I don't know if you are familiar with this big name. In iterative Chidume, Charles, he died a few years ago. He was a good friend of mine. He was from Nigeria, but he spent almost all his career in ICTP Trieste, Italy. Yes, and he invited me many times. I was able to visit him only twice. Also Trieste, so ICTP Trieste comes from International Center for Theoretical Physics, where it's a lot of mathematics in theoretical physics. And he was working there. His PhD student, I guess this name, in 1998. So if you look 1977, more than 20 years. He proved that these two conditions are equivalent in a Hilbert space. So be careful in a Hilbert space. And when I visited Chidume first in Trieste in 2004, he told me how he did his PhD. He did his PhD in an unusual way. He was enrolled as a PhD student. I don't remember the name of the university in USA, a good university in USA. But the group there were working in totally different areas. And he said, no, I want to work on this topic, iterative, fixed point iterative methods. And they said, we are not familiar. We are not familiar. You should go to another university and find a supervisor appropriate for this topic. But his supervisor, which was not working in this field, said, but we do accept the following situation. If you publish 2 papers in very high ranked journals, then we accept your thesis. And he did. He published very nice papers, even in proceedings of American Mathematical Society, and this was his main. He actually has the that he studied k-demicontractive mappings, but in Banach spaces. In Banach spaces, these two conditions are not more equivalent. And he used this definition in Banach spaces, not this one. We can write this in Banach spaces too, but he used this. This is more appropriate, but what is needed to put instead the inner product in a Banach space? There is no inner product, so is the duality mapping. And he produced a lot of very nice mathematics. He has a monograph, by the way, published in Springer about his results. He produced a lot of good mathematicians in Nigeria. And just to tell you then, we spoke, he told me he started from this paper by Marușter. And I said, Marușter, it's a professor in Romania. Ah, is he Romanian? Oh, is he alive? Yes. And next step was he wanted to know Marușter. He gave him the topic of his research work, because all his life he worked on this kind of problems. And he said, I want to know Professor Marușter. He visited me first, and then we went to Timișoara to know Professor Marușter, and they even wrote 1 or 2 papers together. Professor Marușter was old. At the time, he was almost 80. And this is the story with these 2 papers. I told you yesterday, I was almost convinced that Hicks and Kubitschek knew this paper. They didn't, because they just enriched use the technique of enrichment for quasi-non-expansive mappings. They had a close look to the paper by Browder and Petrichin. Browder and Petrichin did for non-expansive to get the class of strictly pseudo-contractive, and they did for quasi-non-expansive to get this class of demi-contractive. And here is the similar proof that in a Hilbert space, the class of demi-contractive mappings is a saturated class of mappings. And the proof is given in the same paper by me and Madalina Păcurar, published in 2021, where we introduce the concept of saturated and unsaturated. And the proof is quite similar. To prove that the class of demi-contractive mappings is saturated, we prove that it is the class of enriched quasi-non-expansive. This is the point. So, till now, we could be happy with the term enriched. This term enriched was useful so far, because we succeeded to discover that these 2 classes are saturated. And we start now, this means it is enriched quasi-non-expansive. We take a map which is demi-contractive. We use the definition. The same tool as before, because we are working in a Hilbert space. And so our condition 2 stars is equivalent to this one. You may see that it is almost the same like in the case of strictly pseudo-contractive mappings. The difference here, we don't have T of Y, here we don't have Y, and also here we don't have Y and T of Y. So this is the difference, and we add the same the corresponding quantity to get a similar inequality, and then by denoting b k over 1 minus k, we get the definition of an enriched quasi-non-expansive mappings. Well, we can understand that at this moment I realized what? I realized that the class of enriched non-expansive mappings that I introduced is the same with the class of strictly projective mappings in Hilbert spaces. In a Hilbert space. Then this was the reason taking the idea of Chidume to introduce enriched non-expansive mappings in Banach spaces. And in Banach spaces, this is not more true, so this is a new class of mappings and it works all the theory. But because I realized that these two classes are saturated, my question was, after a while, you know, after you are disappointed of something, you need some while to recover. I said, these are not important. I left aside this work, and I said they are not important. But after a while, I put myself this question. However, are there any benefits of the fact that this class and also the class of strictly pseudo-contractive mappings is saturated? And yes, there is a huge, huge benefit. And you'll see. What happens? Any result regarding the convergence of a fixed point iterative scheme designed to approximate fixed points of demi-contractive mappings in a Hilbert space can be derived from the corresponding convergence theorems in the class of quasi-non-expansive mappings. This is the result in this paper. This result was included in this paper. What does it mean? How is this possible? So look, we start from a class, let's say in that case from the class of quasi-non-expansive mappings, quasi-non-expansive, and we have a theorem, let's say theorem 1. For an algorithm, a certain algorithm and a certain class of map. And we can get, for demi-contractive mappings, the same results if we have here a map T, let's say, and if we have here a map U. And so we can extend this theorem to the larger class of the demi-contractive mappings. It's very easy. How? If U is here, then there exists a lambda, maybe 0, 1 strictly, such that U is, and a T in QNE, such that U is T lambda. And so we embed all these mappings into the class of quasi-non-expansive. This one is quasi-non-expansive for some values. And so we can prove. In this paper, I proved the results by Hicks and Kubitschek and the results by Maruster by this embedding. We embed the class of demi-contractive mappings in the class of quasi-non-expansive mappings. And the main, the main point is here that we have these two lemmas which are important for us. In that case, for demi mappings. If we are in a Hilbert space, H, and C is closed and convex, T is a K demi-contractive mapping, then the average T lambda, the map T lambda is